Okay, so good evening, everyone. We will start week number 5 and we will solve assignment 5 and assignment 6 in this live mentoring session only. Okay, so let's start. So, in assignment number 5, it is a three truss member where lengths are different and Young's modulus are same and areas are also varying, and there is a horizontal force is acting at node number 5, and it is also given stiffness matrix, element wise stiffness matrix, and it is also saying that we need to consider these as a nodes and these are element connectivity. Let's solve this problem. So from the variational form, we already know that for the truss problem, so this is the variational form 0 to L, or you can say if it is in domain, then we write this AE dV by dx du by dx into dx equal to VAE du by dx and the domain. Okay, so for the element wise operation, we already saw that VE can be written as N V hat E, UE can be written as same as V hat E, X E is N X hat E, and du E by dx E can be written as B by J U hat E, and similarly dVE by dxe can also be written B by J VE. Okay, and dx can be written as a Jacobian times d zeta. Okay, so we already know that N is nothing but the safe function matrix, J is Jacobian. Okay, so when we substitute this in this variational form for the element wise, then we already got that VE transpose that will be -1 to 1 AE B transpose B divided by J d zeta times U hat E, and on the right hand side we write V transpose E, and this one is the N transpose AE du by dx, and that will go from -1 to 1. Okay, so this is the variational form when we substitute here. So we can separate, since V transpose E on the left hand side and right hand side are same, so we can write as -1 to 1 AE B transpose B divided by J del zeta, and this will be UE, and this will be N transpose AE du by dx -1 to 1. So this is the form where we can use for each element, and here we can see that this is nothing but the element stiffness, okay, element stiffness we can write, but this is not in the global coordinate, okay. So here we need to take care of, okay. So this will be also E underscore I will write, and this will be Fe underscore, okay. So when we convert when we convert this element wise stiffness matrix in the global coordinate axis, which is nothing but this x y axis, okay. So to transform this K, we already saw in the class, if we want to transform this element wise stiffness matrix which is in the local coordinate axis, we can write Ke, okay. I will not write underscore because I will use the global coordinate axis. So I can write Q transpose K underscore E Q, okay. So we already saw that this will become like this form, AE by L, and this is L square Lm minus L square minus Lm M square minus Lm minus M square L square Lm, and this will be M square. Since it is a symmetric, so whatever this upper part is there will be lower part also, okay. So when we assemble, now this is in the global coordinate axis, okay. So if we want to assemble, now if we want to assemble this with all elements, so this becomes K global, okay. And this K global is the nothing but the summation of all matrices, and we will write E equal to 1 to the number of element and Ke, and we need to take care of all the indices accordingly, okay. Similarly, F global becomes E equal to 1 to N and Fe, okay. So it will become Fe, and U we can write as U equal to U1, U2, U3, U4 dot dot dot, and this will become, if there are 3 elements, then it will become U6, okay. If it is a 4 element system, then it will become U8, okay. Now let's see how we will solve this problem, okay. So before going to that, we will take care of whatever the problem is saying, which means that we need to see how nodal coordinates and how element connectivities are given, okay. So in the given problem, it is saying that we need to write node and its coordinate, okay. So it is saying that for node 1 the coordinate is 0, 0, for node 2 the coordinate is 0.3, 0, for node 3 it is 0.6, 0, and node 4 it is 0.3, minus 0.2, okay. And also we need to see how elements are connected with the node number, okay. So element and node connectivity, okay. So we will see that element number 1 is connected with 1, 4 nodes, element 2 is connected with 2, 4 nodes, element 3 is connected with 3, 4 node number, okay. So this is the problem, okay. And here we also need to take care of how the area is changing, because there are 3 areas, I mean 3 truss members with 3 different areas, and lengths are also different, and P, which is a force which is acting on node number 4, okay, which is in the horizontal direction. Okay, let's solve this problem in the MATLAB. So this is the assignment number 5. So as I already told you, so here you can see that the node number, this is the node coordinates. You can see that this one 0 0 is nothing but the nodal coordinate, which is node 1, and for node 2 it is 0.30, for node 3 it is 0.60, and for node 4 it is 0.3 minus 2, and here it is the connecting elements. So this one is the element 1, which is connected by node 1 4. This is element 2, which is 2 4. This is element 3, this is 3 4. Okay, and also for each element area is changing. So here for element 1 it is 0.02 meter square. Area element 2 has area 0.04 meter square, and for area for element 3 it is 0.01. And modulus of elasticity is also given, that is 70 megapascal. So what I have written is, everything I have written is SI unit, so I have converted megapascal by multiplying 10 raised to the power 6 to convert into Pascal. Okay, and also here we need to take care of how the fixed coordinates are given. So here we can see that there is only 2 degree of freedom, okay, because at node 1 u1 and u2 is 0, at node 2 u3 u4 is 0, at node 3 u5 u6 is also 0. Only at node 4, which is u4 and u8 survives, so that's why the degree of freedom in this case is 7 8. Okay, here n is nothing but the number of nodes. So I can get by using the size function NDOF. Okay, so we saw that whatever the number of nodes, it will be 2 times. Okay, because for one node it has displacement along x-axis and displacement along y-axis. So that's why we need, for each node we need 2 degree of freedom. So that's why I have multiplied it. And NE is the number of elements. Okay, now I have to initialize the global stiffness matrix, that is nothing but 0 0. It will be a square matrix, and it will be NDOF comma NDOF, and F is a force vector, that will be 0 NDOF comma 1. Now we already know that forces are already given. Okay, forces are already given because we don't know what is the value of F1 F2 F3 F4 F5 F6, but one thing we know that it is given F4 as here at node 4 F5 is value is P, and F6 it is 0. Okay, so here we can see that I can write F7 and F8. Okay, so it should be F7 and F8. F7 and F8. So it is given that F7 equal to P, so I have to write F7 equal to P value. So what is the value of P? It is given 16,000. Okay, so I have written 16,000, but here I need to change, so that is F8. So F8 value is 0. Okay, that is the load at node 4. Okay, that is the 0 because there is no vertical force at node 4. Now for each element, we saw that for each element area is changing. Okay, and for each element according to the nodal coordinate, here x1 y1 x2 y2, it will give a coordinate of 2 nodes for one element. Okay, so accordingly it will calculate L. okay, capital L, that is nothing but the length of the bar, okay, and here L is nothing but the cosine of the angle, cosine of the angle of that particular bar, and M is the sine, okay. So here we will get capital L, small l and small m, okay. Now we can print what is the value of L and M corresponding to particular element, okay. So and here also, as we already saw that this will be the stiffness matrix for that element, so we can write exactly whatever I have written here. So it will print global stiffness matrix for that corresponding element, okay. And then accordingly we already saw that for node number 1 this will be the nodal coordinates, okay. So accordingly it will add, because initially these values are 0, so it will be added up, okay, when this loop runs, okay. Then we will get, after completion of this loop, we will get the global stiffness matrix, and it will be saved in the capital K, okay. Now we have to find how displacement we will get, okay. So we will first initialize the displacement as a 0 vector, and then we will store K reduced and F reduced accordingly when the displacements are 0, so which are nothing but the 1, 2 and 3 nodes. So accordingly I have written that particular node, okay. Then we will print the nodal displacements here, and then we will find what are the reaction forces at each node. Now this code is to find the stress and strains for each element. So you can see that this is nothing but to calculate the strain, that will be B times displacement, and for stress it will be E times strain, okay. Now let's run this code. Okay, so here it is a stiffness matrix for element 1, okay, and here it will be a L and M values for element 1. So it is clear that when we put origin here, then definitely L is nothing but the cosine, so that will be 0.8 through T1 and minus 0.5547, okay. Okay, so similarly for element 2, this is the L and M value, and this is the stiffness matrix for element 2, and this is the stiffness matrix and L and M value for element 3, and this is the global stiffness matrix, and this is the reduced stiffness matrix, this is the reduced force vector, and this is the result for the nodal displacement. So here for node 1 we can see that there is no displacement in x and y direction. For nodal 2 it is also 0, for nodal 3 it is also 0, but for nodal 4 we can see that there is a displacement along x and y direction, okay. And this is the reaction force, and this is the element strain and stresses, okay. So this is all about the solution for the assignment number 5, and then we will try to match all the problems which is given in the assignment number 5. Now we will run this code, and we will see the result what we are getting. One thing we need to take care of, which is the element connectivity, okay. Otherwise there will be a problem in the sign convention of getting L and M values. Okay, so here you can see that it is already given that for element 1 we need to use 4 1 node, and for element 2 we need to use 2 4, and for element 3 we have to use 3 4. Okay, so here one thing we have to understand that there is no such problem if we, so if you swap like node 1 and node 4. Okay, like for here 4 first and 2 second. Okay, because when we try to get this stiffness matrix, there is no such problem of getting element stiffness matrix, but here when we try to get L and M value, there will be a problem with the sign convention. So that's why we have to use whatever in the problem it is given. So here we have to use the same. Now we will try to match the solution we are getting. So here we can see that what is the value of L and M for element 1. So it will be minus 0.8321, 0.555. For element 2 it will be 0 comma minus 1. For element 3 it will be minus 0.832 and minus 0.555. Now it is saying what will be the size of the global stiffness matrix. So here we can see that it should be 8 by 8, and here now it is saying what will be the global stiffness matrix after imposition of the boundary condition. This problem means that where we have to impose the boundary condition. Okay, so it is clear that at node 4 we have to impose the boundary condition. That's why the answer will be D. Okay, now it is saying for the element let the global stiffness matrix after the imposition of the boundary condition, then what will be the K11. Okay, so let's see what is the case. Okay, so for element K11 after imposition of the boundary condition, what will be the K11. So here we will see after the imposition of the boundary condition. So where is that? Yeah, here after the imposition of the boundary condition, this 4 by 4 matrix it is saying. So it is clear that for K11 element K11 it will be minus 4032, since the solution is will be multiplied by 1 into 10 to the power 7. So that will be this will be the correct answer, 4.03 into 10 to the power 6. Now for the same element it is saying what will be the K12. So this will be the K12. Okay, this is the answer. Now it is saying K22, this is the K22. Okay, yeah, this is the K22. Now it is saying let the load vector after the imposition of the boundary condition will be. Okay, so we will see, yeah, we will see where we impose the boundary condition. So it's clear that only in x direction. Okay, in only x direction we are imposing the boundary condition. So that's why for that part that 16,000 will be the answer. So it is saying what will be the value of f22, sorry f2, so that will be 0. Now it is saying if we multiply ku with f, I mean the global stiffness matrix times displacement equal to f, then what will be the condition. Okay, so it is saying at the loading point. Okay, so we will see the nodal displacement. So this is the loading node. It is saying what is the horizontal displacement. Okay, so this one is the horizontal displacement. It is saying in the mm, so we will omit this part. Okay, so this will be the answer. And now it is saying what is the vertical displacement at the loading point. So this is the vertical displacement. Okay, so since we have to multiply with 10 raised to the power 3, so first decimal will go inside. Okay, so this is all about the solution of assignment 5. Okay, now we will try to implement the MATLAB with the class problem where sir has discussed. Okay, So yeah, so this was the class problem, and after that we will go for the assignment number 6. Okay, so let's create this. Yeah, so before moving to that, we will try to understand how we will formulate how we will formulate for the beam problem. Okay, so okay, so let's try to understand this problem, then we will go for the solution. Okay, so we already know that this is the governing equation we use in the beam problem, that is d2w by dx square equal to minus m times ei. Okay, so when we move it, we will get m equal to ei minus times, that will be minus times ei d2w by dx square. Okay, so this is the moment equation we use. Okay, and we also know that q equal to minus dv by dx, and also we know that v equal to dm by dx. Okay, so when you substitute this here, so first we need to differentiate it, so it will become v equal to d by dx. Okay, and minus sign will come into the picture, and ei d2w by dx square. So to get q, we need to again differentiate it, so it will become q equal to, and this minus term will get absorbed, so it will become 2 d2 by dx square and ei dw by dx square. Okay, so after rearranging, it becomes d2 by dx square ei dw by dx square and minus q equal to 0. Okay, so also we need to take care of some sign convention. So in this problem, the sign convention was, when forces are downward, we have to take positive; when moment are clockwise, we have to take positive. Okay, so this is the boundary condition we have to take care of. Okay, so let's see what is the variational form of this differential equation. So the variational statement was like this. So that will be 0 to L and v d2 by dx square and ei d2w by dx square dx equal to 0 to L and v q dx. Okay, so this is the variational statement. This is the variational statement. Okay, so after the integrating by parts, we saw that we get this equation. What is that? This is 0 to L ei d2v by dx square d2w by dx square dx equal to 0 to L vq dx, okay, plus this part I will take separately. So this will be dv by dx ei d2 by dx square, and this will be 0 to L, and minus v d by dx ei d2w by dx square 0 to L. Okay, so we already know that this is nothing but the natural boundary condition, and this was all about the essential boundary condition. Okay, so now we know that for each node we will have two kind of displacement we are considering, okay, which are w1 and w1 dash. Okay, so for each node, here if it is node 1, so we need to consider w1 and w1 dash. Here also there is a sign convention, that is if w is downward then we have to take positive, and when rotation is clockwise, that will be also taken as a positive. Okay, so this is the sign convention. So for any element, okay, so for any element we need to write this form of displacement equation, okay, w1 w1 dash, w2 and w2 dash. Okay, and we saw that w in terms of zeta we can write that will be n1 w1 n2 w1 dash plus n3 w2 plus n4 w2 dash. Okay, and after solving everything, and since we are using the Hermite polynomial, Hermite kind of shape function, so we saw that for the Hermite shape function we saw that n1 we have to use 1 by 4 1 minus zeta raised to the power 2 2 plus zeta, n2 we need to use 1 by 4 1 minus zeta raised to the power 2 1 plus zeta, n3 we have to use 1 by 4 1 plus zeta square 2 minus zeta, and similarly n4 it will be 1 by 4 1 plus zeta raised to the power 2 zeta minus 1. So this is the shape function, we have to use it directly. Okay, now we saw that we have to substitute d2w by dx square. So okay, so we need to substitute d2w by dx square, that will be exactly same as a d2b by dx square. So in that case we already saw that d2 by d2w by dx square we can write 4 by le square, and this will be d2n by d zeta square and w e vector. Okay, and we have to substitute n as a so that we also discuss what kind of w we will use. So this kind of w we will use, so when we transform this, then we get this. Okay, so so after differentiating n, whatever we wrote it, so it becomes dw by dx square, that will be 4 by le square, and it will be 3 zeta by 2 le by 4 3 zeta minus 1 and 3 zeta by 2 le by 4 3 zeta plus 1 and w e vector. Okay, and similarly we have to use v zeta also like this, and this we call it as a b. Okay, this this thing we will call it as a B. Okay, now, and we have to use the displacement, or not displacement, the x coordinate. Okay, we have to use the x coordinate same as a Lagrange shape function. Okay, we will not use Hermite shape function, so we will use the same. So this thing is little different, as we solved as a beam problem, not beam problem, bar problem, and that truss problem. Okay, so yeah, after substituting everything here, so after substituting everything, we get elemental stiffness matrix, which was EILE by 2 and minus 1 to 1, 16 LE raised to the power 4, and okay, here there is a mistake, EILE by 2, and it will be B transpose. It will be B transpose B, B transpose B d zeta. Okay, so this is the stiffness matrix. Okay, so after writing everything, we get VE transpose KE, and it will be WE, and that will be force vector, I mean VE transpose force vector. So this kind of form we need to use, so that will be nothing but KED equal to FE. Okay, now let's move to the problem where we have given to solve. Okay, so before moving to that, we will note every data which was given. So the data was L1 equal to 2 meter. Okay, L1 equal to 2, yeah, L1 equal to 2 meter, L2 equal to also 2 meter, L3 equal to 1 meter, L4 equal to 1 meter, E equal to 210, GPA, I is 0.5 into 10 to the power minus 6 meter raised to the power 4, F, that is the concentrating load, that was given 10,000 Newton, and moment that was applied at the rightmost, and not rightmost, at node, so 1 2 3 1 2 3 4 node. Okay, fourth node. So M was applied, that was 3000 Newton meter, and that shear, not shear, that was the distributed load. Okay, uniform distributed load was also applied, that is 2000 Newton per meter. Okay, so this is the data which is given. Now let's move to the code which I have written. Okay, okay, so this was the problem. So in this code, we need to first create the mesh. So that is at the node 1, the coordinate is 0, node 2 that is 2, node 3 that is 4, 5 and 6, and this is the element connectivity, that is 1 2. Okay, this is the element number 1. Okay, this is the element number 2 where the element connectivity is 2 3, and this is the element number 3 where the element connectivity is 3 4, and this is the element 4 where the element connectivity is 4 5. Okay, now this is the number of element we will get by using the size function, so it will give 4, and this is the degree of freedom. okay, whatever the length of x, okay, so here the length of x is 5, so we have to use 10 degree of freedom, okay, because at each node there is a 2 degree of freedom, okay. So we will first initialize the global and force matrix, and here for each element it is given the same Young's modulus. So we need to create for 4 elements we have to write E as a 4 elements, and similarly moment of inertia is also given, okay. Now for each element we have to provide the Young's modulus and moment of inertia. So I will, yeah, stiffness matrix and force matrix, yes. Yeah, so for to find the k local, okay, to find the k local we will see how this value we will get. So first it will take the local coordinate. So for element 1 that is nothing but 0 2, okay, this is the local coordinate, and modulus of elasticity that is the first element of elasticity, and moment of inertia that is the first element. So when we see the compute stiffness matrix function, here we have written symbolic as xi, okay. So it will take the local coordinate, the length of the element by using the nodal coordinate 2 and 1, okay. And this is the shape function matrix, and we will see what is the shape function matrix we are using. Yeah, this is the shape function matrix we are using. This is the derivative actually, so we will not see that derivative, we will see the shape function matrix. So here we can see that this is the shape function for the Hermite cubic polynomial, so it will return n1 n2 n3 and n4, okay. So after getting the shape function matrix, we need to also differentiate, the shape function matrix twice, okay. So that's why I have written this, and this is the B, okay, this is the B which we have already written, okay. So this is the B, where it is, yeah, so this is the B, okay. So here you can see that it will differentiate twice and 4 by LE square, and this is the all elements, okay. So here you can see that, so after getting it will becomes like this. So this is the don't confuse with this, when you differentiate it, it becomes like that only, okay. So here, but what I have done is I have written the same form whatever sir has used, okay. So after differentiating and every term substituting, we will get this form, okay. And then we will localize, we will initialize the local stiffness matrix, and we are using the Gauss quadrature point with the fourth polynomial, okay, fourth order, okay. Then here you can see that it is nothing but the EI LE by 2 and B transpose B, okay. So we already saw that will be where it is, yeah, this one, EI LE by 2 B transpose B, okay. And this will be added up according to the number of points which we are considering for the Gauss integration, okay. So this was all about the stiffness matrix. Now we will move to the force matrix, okay. So the force matrix we will use the boundary condition where we have given. So here we already saw that there is a boundary condition, not boundary condition, this is the uniform distributed load, okay. So it is a uniform distributed load. We can see that uniform distributed load is only acting on element 2 when the nodal coordinate is 2 and 4. So that's why I have used when the nodal coordinate is 2 and 4, I have used the UDL. Otherwise, on other elements, nothing is there. No UDL is provided. Okay. So now we will use the compute force matrix. Okay. So where it is compute force matrix? So here it is. So compute force matrix will take the nodal coordinate and Q value. Okay. So here this is the compute force matrix. This is nothing but the same thing which we have already discussed. that is the V. So that is nothing but the N transpose. Okay, that is nothing but the N transpose and Q. Okay, and then it will integrate, because V transpose will go outside of the integral. Okay, yeah. So this is, yeah, this is the N. Okay, N whatever we used, N transpose, then it will be multiplied Q into LE times N transpose. Okay, so this will be the force matrix. Okay, then after running this loop, we'll get the localized, and after the completion of the loop, we will get the global. Okay, now we will put the boundary condition here. The boundary condition is at point x equal to 2 and at x equal to 5. Okay, so here boundary condition is here and here. Okay, so that's why I have kept point load as active at x equal to 2 and moment at x equal to 5, and it will be added in the F global. Okay, then it will print, and now we will solve the matrix equation, that was K global D times F global. Okay, before that we need to create the reduced K reduced matrix and F reduced matrix. So from the global stiffness and global force matrix, it will remove the nodal, it will remove the nodal index from the rows and column. Okay, so it will give K reduced and F reduced. So after solving this, we'll get this. Okay, and then it will fill into the displacement nodal coordinate matrix. Okay, now we will post process. Okay, after solving this, so let's solve up to this point. Okay, so these are the solution: stiffness matrix 1, stiffness matrix 2, 4, global stiffness matrix, everything we get it. Okay, now we will do the post processing. So for post processing, we know that for each element we need to vary xi value from -1 to 1. So I have used the lean space function. It will create all xi value -1 to 1, and it will give 15 elements, 50 such element. And also I have initialized displacement vector, slope vector, moment vector, and shear plot vector and x plot. Okay, so here in this first it will take a local coordinate, then it will calculate length, that is LE. Okay, and here to calculate the stiffness displacement, first it will calculate n dn, and I will tell you why I am using the triple D, single D like that. Okay, this the main purpose of use the triple D, which means that we need to differentiate three times n to get the force. Okay, to get the shear force. And here why I am using why I am differentiating twice to get the moment. Okay, why I am using the single time derivative to get the slope. Okay, so that's why I have differentiated one time, two times, second time, and three time to n, and then I'll substitute xi value for each n matrix. Okay, by multiplying 2 by LE. And here you can see that I have to multiply to get the moment, I have to multiply 4 by LE square. To get the shear, I have to multiply 8 by LE cube. Okay, and then to get the displacement, I will multiply n times displacement. Okay, n time displacement to get the m times whatever the element wise we got it. And now it now it is in the that physical coordinate. Okay, it will be in the physical coordinate. Earlier it was in the master space, now it is in the physical space. And here it is a x local, that is the Lagrange basis, and then we will plot the displacement and slope plot. And also we compared the nodal coordinate and what will be the continuous. If you assume the continuous beam, then by using the interpolation, this is the nothing but the interpolation method, and I use the post processing, then we will see the result what we are getting. Okay, So yeah, so here you can see that we only got 1 2 3 4 5 nodal coordinates, okay. And here you can see that this continuous graph is nothing but the interpolation or continuous solution, and here it is the nodal solution we got by using the finite element, okay. And here it is the slope, the plot of slope versus x, okay. This is the same as whatever sir has got in the lecture. So yeah, now if we analyze it, if we analyze the slope, if we analyze the slope, we can see that figure 1 also, we can see that the displacement at node 1 and at node 1 2 3 4 5 node, it is both are 0, but here it will be the maximum, okay. And also we can see that the slope will be positive, the slope will be positive because we are considering in the clockwise direction, because the beam will bend like this, so that's why we are getting the positive slope. And here also the positive slope, no, not positive, here we will get the negative slope because it will bend something, okay. So that's why we are getting this solution, okay. So this is all about the class problem. Now we will move to the assignment 6 problem, and we will try to solve that thing also, and we will use the same theory whatever we discussed for the assignment 5, okay. Not assignment 5, the class problem, okay. So this is the assignment 6. Now here we can see that we have to use only two element. This is the element number 1 and this is the element number 2, and this is the meshing, that will be 0 0.1. we can see that we have to use L equal to 0.1 meter, L2 equal to 0.2 meter, so that's why I have meshed 0 0.1 and 3. And this is the element connectivity 1 2 2 3, and this is all about this is same, these are all same, and but we have to use different elastic modulus is same for both elements, but moment of inertia are different. So here you can see that will be 200 gigapascal, and this is the moment of inertia for two different elements, and these are same. Now we have to change the UDL condition. So here you can see that for element 1 only the UDL is applied. So that's why when local coordinate is 0, I mean the first element of the local coordinate is 0 and the second element of the local coordinate is 1, which means that for this element only we have to apply the UDL condition, okay. So what is the distributed load here? The distributed load is 500 Newton per meter, so that's why I have written 0.5 e raised to the power 3, and at another element there is no such UDL, okay. So these are same. Now we will apply the Neumann boundary condition. What is the Neumann boundary condition? The Neumann boundary condition is when x equal to 2, not x equal to 2, this is the misprint, I mean I have used the same code, so that's why I have written. So that will be when x equal to 0.1, x equal to 0.1, the point load is 1000. So what is the value of F? Yeah, 1 kilonewton. And when the value of L is 0.3, okay, the value of L is 0.3, 0.1, 0.2, yeah, 0.3, the moment is 5000, okay. So yeah, so now I will apply the Neumann boundary condition in the global force matrix which I got here. So we will add this up, but only third element and sixth element, I mean the third coordinate and sixth coordinate, because this is the coordinate number 1, okay. Coordinate number 1 and coordinate number 2 is hidden here. Now coordinate number 3 is the force, so that's why I have added point load here, but there is no such moment applied here, so that's why I have not using the F global 4. Similarly for node 6, not node 6, for coordinate 6, okay. For coordinate 5 is unknown, but coordinate 6 it is given that boundary condition is moment, that is 5000, so that's why I have added here. Now the fixed node, which are the fixed nodes? Fixed nodes are at point A, okay, so that's why I have used 1, 2, okay. And also the fixed node is at point C, so that's why I have used 5, okay. 5 why I have used, because the displacement boundary condition is 0 at node C, but uh, the slope is non-zero, so that's why I have not used 6. So this will separate the free node from the whatever the mesh we have used, and it will get the k reduced, f reduced, and it will solve the problem. Okay, and then we will use the post processing. This thing will not change, and whatever we got, it will remain same. Now we will run this code. Okay, and we will see the results. Okay, okay, and we will compare the results which we got. Okay, I think I should not reveal the answer because due date is 6 September. Okay, so I will not reveal the result. You should see the results by yourself. Okay, but yeah, we will analyze the result. Okay, so this is the displacement. Here you can see that there is no such displacement at point A, and there is no such displacement at point when x equal to 0.3. Okay, and the maximum displacement is near 0.18 something, and that is minus 0.005. Okay, so which means that this beam will go up, which means that the beam will go up, so that's why it is something like this. Okay, and this is the slope diagram of slope. So here you can see that there is no such theta. I mean, this beam will not rotate at point A, so that's why the slope is 0 here, and the slope is maximum when L is 0.3. Okay, and we will analyze the global force matrix. So here these are the force matrix, and this is the reduced and nodal displacements and reaction forces. Okay, so these are all about the solution to the assignment 5 and assignment 6, and also we have discussed the class problem by using the same code which we have created. Okay, so yeah, so let's see next week, and we will try to solve the assignment 7 also. Thank you.